Welcome to this sailing theory tutorial. My name is Julian. In this video, we're talking about sailing in current and tides. So in this video, I plan to present to you a simple model of how current will affect a boat's motion through the water. We'll take a closer look at the flow over sails and foils when current enters into play. And in a future video, we're going to take a stab at predicting tidal current, direction, and strength from the tide tables. And at the end, I'm going to give you some racing strategy examples involving current. So let's get started with our simple model. We're going to call the technique that we're using to analyze this model relative motion. Now that name begs a certain question. Relative to what? And so what I'm going to answer that with is the word, the ground. And for the purposes of this segment, we're going to talk about the ground, and we're going to basically say that the ground is a non-moving object, like the shore or the sea bottom. Okay, so let's mark a point on shore. We'll call it G for ground. I'd like you to consider for a second a boat that starts off at that point G and sets sail into still water. By still water, I mean water that's not moving. There's no current yet. We could pull out a stopwatch and start it the moment that the boat departs, and we could run that stopwatch as the boat moves through the water. After some time, the boat will have moved a set distance, and it will have moved in a direction of an arrow that points from G to point B. We're going to draw point B on the boat. So we can take the distance that the boat moved and the time that we have on our stopwatch and use that to calculate a speed that the boat was traveling. We can also take the direction that the boat was traveling from that arrow. If we combine the speed and the direction, we have enough information to make a velocity vector. Let's label the velocity vector here V, B, G. And in this case, BG is going to refer to the velocity of the boat relative to the ground. So here's a trick for you. I said earlier that we were referring to the ground as something that doesn't move. And because the water in this situation is still, we have no current, we can actually say that it doesn't move either, and that the velocity of the boat relative to the ground is equal to the velocity of the boat relative to the water. This is not something that's going to be generally true, and it falls off as soon as we have current. But for now, let's just copy that vector and relabel it as the velocity of the boat relative to the water. So for now, I'd like to ignore all of the other conditions like wind speed, waves, maybe the skill of the sailor, stuff like that. And I want to say that the velocity that the boat moves through the water is a property of the boat. So if you pick the boat up, you put it somewhere else in another position, it's still going to move with that same velocity through the water. Okay, so if we can internalize that concept, I'm just going to stick the boat off to the side for now. We'll start talking about current. Okay, now we're going to deal with another situation where we do have current. So this is a condition where the water is going to be moving. I want to imagine that we have some observer, and that observer is going to stand next to point G. And that observer is going to throw a rubber ducky into the water, and at the same moment that they throw the rubber ducky in the water, they're going to start their stopwatch. They're going to watch the movement of the rubber ducky, and after a certain amount of time, they're going to stop their stopwatch, and they're going to keep track of where the rubber ducky ended up. They keep track of the position of the rubber ducky. Then they can take the distance that it moved, divide it by the time on their stopwatch to come up with an average speed of the current. If they watch exactly where the rubber ducky moved, then they know the direction of the current as well. So in this way, we could come up with a velocity vector for the current. And we can call that velocity vector the velocity of the water relative to the ground. We can label that VWG, where W is for water and G is for ground. So now I'm going to bring the boat back on scene, and I'm going to ask you, what velocity will the boat have relative to the ground if it's sailing in current? In other words, to the observer on shore, what velocity is the boat going to have? We're going to give that velocity a name, and we'll call it VBG, where B stands for the boat and G stands for the ground. And I'm going to tell you the answer too. We're going to find the answer to that question by adding the velocity of the boat relative to the water to the velocity of the boat relative to the ground. So we're going to take VBW and add it to VWG, tip to tail, like always. And if we draw a vector arrow that connects the tail of VBW to the tip of VWG, we'll have our vector VBG. And this vector arrow is going to represent the velocity of the boat relative to the ground. Again, in other words, that's going to be the velocity that the person standing on the ground would perceive that the boat is moving. So something that we can take away from the direction that these arrows are pointing in is if we remember that the green arrow was pointing in line with the bow of the boat, but the boat traveled along the red arrow, the boat is going to travel in a different direction from the direction where its bow is pointing in a situation where we have current. Also, from the differences in the lengths of these vector arrows, something that we can take away is that the speed of the boat is going to be different when we have current. Now I'm saying different here instead of greater, because whether it's greater or less than the original speed is going to depend on the direction of the current, and we're going to see that in a second. I'd like to reinforce what we've been talking about with a couple of examples. For each of these examples, let's consider a constant uniform current that's flowing in the direction from the top of the page. We'll draw it in purple and call it VWG. For the first example, I'd like to consider a boat with a known velocity through the water sailing directly against the current. The question that we'd like to answer is, what is the boat's velocity with respect to the ground? We'll draw the boat's velocity with respect to the water in green. We'll add it to the velocity of the water with respect to the ground, which we drew in purple. And we'll connect those vectors tip to tail and draw our new vector from the tail of the first to the tip of the second. And our VBG is this red vector here. So we can make a couple of observations here. One of them is that the direction didn't change. The red vector is pointing in the same direction as the green vector. The second observation that we can make is that the speed of the boat would be reduced in a situation where it's sailing against the current. And this is reflected by the shorter length of the VBG vector. For our second example, let's look at a boat that's sailing at an angle against the current. Again, we'll draw our green VBW vector and add it to our purple VWG vector. Our red vector, which represents the boat's velocity with respect to the ground, is from the tail of the green vector to the tip of the purple vector. A couple of observations that we can make here is that the direction of the red vector is turned downstream of the green vector. We'll also notice that the length of the red vector is shorter than the green vector, and this indicates that the speed of the boat again is reduced when we're sailing against the current. For our third example, let's think of a boat that's sailing at an angle downstream or with the current. We'll take our green VBW vector and we'll add it to our purple VWG vector. We'll draw our new red vector, which represents the boat's velocity with respect to the ground, from the tail of the green vector to the tip of the purple vector. And we can make a couple of observations. First of all, the direction of this red vector is turned downstream again. Secondly, in this case, the length of the red vector is longer than the length of the green vector. So we would say that the speed of the boat is increased when it's sailing at an angle downstream with the current. In this last example, let's think about a boat that's sailing directly in line with the current downstream. We'll take our green VBW vector, add it again to our purple VWG vector. We're going to draw our red vector from the tail of the green vector to the tip of the purple vector. And now we can see that we have a vector that represents the boat's velocity with respect to the ground. We'll make the same observations about this. So, first, the direction of the red vector is identical to the direction of the green vector, so the direction is unchanged. Second, the length of the red vector is longer than the green vector, so we would say that the speed of the boat is increased when it's sailing downstream. So if we were to generalize these observations across all of those four examples, we could say that the direction that the boat will travel is turned downstream unless you're sailing directly in line with the current. We could also say that the speed of the boat with respect to the ground is decreased when sailing against, and it's increased when sailing with the current. Okay, so now I want to give you a practical example of something that you might actually do if you were navigating, say, a keelboat with a paper chart and, a pen and paper. Okay, so we'll start off, we'll say two common instruments on a sailboat are a compass and a knot meter, or a speedometer. Okay, now speedometers can work in one of a few ways. So some common ways are to have either a paddle wheel, which is going to rotate in the water as the boat moves through the water, or something called a pitot tube, which is going to work based on the pressure of the water as the boat moves through the water. Both of these devices are going to read in speed through the water, which is roughly equivalent to VBW. Another way that you could get speed information if you're on a boat is with a GPS or with a sonar transducer. So these two devices would be reading in terms of speed over ground, or VBG, like we were talking about previously. So let's say, for example, that we have a GPS and a paddle wheel knot meter, and we also have a compass. Let's say that the GPS tells us that we're moving at 4 knots in the direction northeast. We can draw our VBG vector like this, and we'll give it the number 4 for its magnitude. Let's say that our knot meter reads 3 knots, and the compass tells us that we're heading east. Okay, so the GPS tells us that we're heading northeast, the compass tells us that we're heading east. Let's find the velocity of the current, VWG. So remember that VWG plus VBW is equal to VBG. We can rearrange that and say that VWG is equal to VBG minus VBW. So if we bring our vector arrows down and we draw ourselves a little diagram, we can actually draw an arrow to represent the velocity of the current. And I've been using the squares on my page here for scale. So if we take a look at this, we can see that our current velocity is going to be approximately 2.6 knots. Okay, so this trick isn't going to be very useful if you're sailing a dinghy, but you can still think about it this way. And the bigger the boat you sail, the more likely it is that someone's actually going to be going down below to keep track of stuff like this on paper or on a laptop. Now I'd like to take a closer look at the current's impact on flow over your sails and your foils. Since we're talking about current, which is movement of water, I think we should start below the waterline. I'm going to borrow a diagram that I first presented in my flow over sails and foils video. So recall that as the boat moves through the water, it makes a certain amount of headway and a certain amount of leeway. And the combination of the headway and the leeway is going to be the boat's progress through the water. So we're going to borrow our label VBW and apply it to that vector. We can move that vector diagram off to the side And since we're talking about the flow over the foils, it's going to be useful for us to turn that VBW vector around. We'll make it face in the opposite direction. And we can label this new blue vector VWB. So, from the point of view of the foils, this is going to be the velocity of the water as it moves across the boat, or the foils. And, from the point of view of the foils, there's going to be some angle of attack, which is the angle between the chord line of the foil and the oncoming flow. And I'll remind you that the foils produce a lifting force perpendicular to the direction of the oncoming flow, and a drag force that acts in the same direction as the oncoming flow. And when we're talking about our foils below the waterline, when we combine the lifting force and the drag force, we end up with a resultant resistance force. What happens when we add current to the mix? Well, let's say that we have a known current, and we're going to represent it by a vector VWG, the velocity of the water with respect to the ground. If we take that current vector and we add it to our original VWB vector, we can come up with a new VWB vector, which I'll draw in light blue here. Bringing the new light blue VWB vector back into the foils, what we can observe is that the angle of attack that the new vector makes with the chord line of the foils is dramatically increased. Thinking back to our forces over sails and foils video, what we know about the angle of attack is that when it increases, it causes the lift and the drag vectors that the foils produce to increase as well. So what we're going to see if we have a moderate amount of current is that it's going to affect the size of our force vectors, or let's say the strength of the forces that our foils are going to feel under the water. If the current was coming in the other direction, hopefully you can visualize that the new VWB vector would shift in the other direction. That would cause the angle of attack to get smaller. And if the angle of attack gets smaller, then the lift and drag vectors are going to get smaller. So like I said before, it's going to affect the strength of the forces that our foils feel under the water. And depending on the direction, the forces will either be stronger or weaker. I'm hoping now that you'll recall from the sail flow, separation, and stall video that as alpha increases, the forces get bigger. But if alpha gets too big, the foil will stall. And when the foil stalls, most of the lift goes away, and the drag increases quite a bit. So I want to examine a situation where we have a very strong current and a boat that's not moving very quickly. So if we go back to our original dark blue VWB vector, and we add to it some large VWG vector, what we can find is a new VWB vector, and we can see that this one is going to make a very sharp angle with the foil. This angle is so big that we would say that this foil is almost definitely going to stall. The impact that that's going to have on the boat is that the lift vector that the foil generates is going to become very small, and the drag vector that the foil generates is going to become quite big. What that means is that the resultant resistance vector, which is the combination of the lift and drag vectors, is going to be pretty large, and it's going to point towards the back of the boat. This means that the foils are not going to be operating very efficiently, and the boat's not going to go very fast. It should be self-evident that we should try not to sail with stalled foils. So, one solution to this problem is to do these things in order. First, we would turn the boat to reduce the angle of attack alpha. So that means that we would have to turn towards the current. Second, we would let the flow reestablish over the foils. So that means we're going to wait a little while pointing in that direction. Third, the boat speed is going to come up because our foils are going to start working again. Fourth, as the boat speed comes up, VWB is going to shift forward again, closer to where it was originally. The last thing that we can do is turn the boat back in the direction that it was heading before, now that it's come up to speed, and hopefully we'll be able to sail without stalled foils. So now let's take a look at what's going on above the waterline in the sails. We're going to borrow another diagram from our flow over sails and foils video. Remember the definition of the true wind, and we're going to define it as coming from the top of the page with this green arrow here. The boat moves through space with a certain velocity that we're drawing in red here. But because we're talking about flow over the sails, it's useful to turn that velocity around, point it in the opposite direction, and call it the boat wind. So if we add the true wind to the boat wind, we obtain a third velocity vector for the wind. We call it the apparent wind. If we move that apparent wind velocity vector over and point it towards the sails, we can see that the apparent wind makes a certain angle of attack with the chord line of the sail. Again, from our forces on sails and foils video, recall that the sails are going to create a lift and a drag force that we can add together to produce an effort force above the waterline. For this next part, we're going to hold the true wind constant, but we're going to go back and find a new boat wind in a situation where we have current acting on the boat. So we'll turn that yellow vector back into a red VBG vector. To that vector, we're going to add the current vector, VWG, representing the motion of the water. And we'll find a new red vector, VBG new, which is going to represent the motion that the boat's going to take with respect to ground when it's traveling in water that has a current. Okay, our next step, like we did at the very beginning of the segment, is to turn the red arrow around and turn the boat speed into a wind speed, basically. We're going to make a new boat wind, add that boat wind to the true wind to find a new apparent wind vector. And if we put that apparent wind vector next to the original apparent wind vector, we can see that it's got a different length and a different direction. So what we can take away from this is that when we're sailing in current, the current can cause changes in the apparent wind's speed and direction. It does that, of course, by changing the boat's velocity. And so, if we wanted to react to the situation that we've drawn here, we should either bear off or sheet in, or of course some combination of the two. This is going to conclude my sailing theory tutorial on sailing in current. In this video, we presented a simple model of how current would affect a boat's motion through the water, and we also took a closer look at the flow over the sails and foils when current enters into play. In a future video, I still intend to cover predicting tidal current direction and strength from the tide table information. And I do want to give some examples that involve racing in current. Thank you for watching.